Let us look at proposition number 2 of book 12 of Euclid's Elements. The proposition says circles are to one another as the squares on their diameters. So C is to D is equal to the square of the diameter of C is to square of the diameter of D. That's what the proposition is saying. So let's proceed. Let C and D be circles and let BD and FH be their diameters. So let's draw these. We have to prove that C is to D is equal to BD square is to FH square. We are going to use proof by contradiction, which means let's assume the contradictory statement. If BD square is to FH square is not equal to an area of C is to area of D, case 1 is BD square is to FH square is equal to area of C is to area S, where area S is less than area of D. So let's bring in that area S. So now the proportion that we have now is BD square is to FH square is equal to area of C is to area S, where S is less than D. Now we inscribe a square EFGH in the circle D. So we have the square EFGH inscribed in the circle D. Now circumscribe a square on circle D through EFGH. So let's do that. Now inscribe the square EFGH is equal to half of the circumscribed square. That is, interior square is half of the exterior square. So inside the square EFGH is greater than half of circle D. Think carefully and have a look at this diagram. Now we bisect the circumferences EF, FG, GH and HE. This circular arcs we bisect, and let's name those points and join these points so that we end up with a polygon. Now draw a parallelogram on FE with the tangent to D at K. So let's do that. So now triangle EKF is equal to half of the parallelogram that we have drawn. Why? Because this triangle and the parallelogram are on the same base and between the same parallel lines. And we know that in such a case, the triangle is half of the parallelogram, which implies triangle EKF is greater than half the segment of the circle about it. Similarly, we can show that triangle FLG, triangle GMH, triangle HNE, they are all greater than half the segment of the circle about them. Now, we keep repeating this process by taking the midpoints again. So we take a midpoint between K and F. We take a midpoint between FL, LG, GM, MH, HN and NE. And we join them. So we get a polygon with 4 number of sides. And actually, in which case it will get closer and closer to the circle, the circumference. And we do this till the segments of the circle combined becomes less than the difference between D and S. Remember, S is less than D. So that means there is a difference. And we keep increasing the number of sides of the polygon till the segments of the circle becomes less than the difference between D and S. Okay, now instead of me doing it because the space is very less, let's assume that we have reached a stage where this condition is satisfied. So let them be these very segments E, K, K, F, F, L, H, G, M, H, M, H, H, N, and N. So which implies polygon E, K, F, L, G, M, H, N is greater than area S. Now we inscribe a polygon on circle C, which is similar to the polygon that we end up with. So let's do that. What this means, these two similar polygons means, is that BD square is to FH square is equal to polygon AOBPCQDR is to polygon EKFLGMHN. Because BD and FH are also the diameters of these two polygons. We also have this BD square is to FH square is equal to circle C area is to area S. So since the left hand sides are equal, right hand sides will also be equal. So circle C is to area S is equal to polygon AOBPCQDR is to polygon EKFLGMHN. Alternately, we can write it as circle C is to polygon AOBPCQDR is equal to area S is to polygon EKFLGMHN. Here on the left hand side, circle C is greater than polygon AOBPCQDR. Yes, because it is the inscribed polygon. So which implies that the right hand side will also have the same property. That is area S is greater than polygon EKFLGMHN, which means we have arrived at a contradiction. How? Because here we said polygon EKFLGMHN is greater than area S. And here we have arrived at area S is greater than polygon EKFLGMHN. So a contradiction, since S cannot be both greater than and less than polygon EKFLGMHN. So BD square is to FH square is not equal to C is to anything less than D. Similarly, we can show the other way around also, that FH square is to BD square is not equal to D is to anything less than C. In this particular case, we took the area S less than area of D. Now let's look at the other case. The other case is BD square is to FH square is equal to area C is to area S, where S is greater than area of D. If possible, let BD square is to FH square equal to area C is to area S. Inversely, we can say FH square is to BD square is equal to area of S is to area of C. Now, area of S is to area of C is equal to area of D is to an area something less than C. It implies FH square is to BD square is equal to area of D is to an area less than the area of C. Again, this particular part, we will look at it as a lemma and we will look at it later, which is not possible, which has already been proved in the previous case. So therefore, BD square is to FH square is not equal to C is to anything greater than D. So finally, we can say C is to D is equal to BD square is to FH square, which is what we had to prove. So now let's look at the lemma part. S is greater than D implies S is to C is equal to D is to something less than C. This is what we have to show in this lemma. Let S is to C is equal to D is to an area T. The T is something less than C. Alternately, we can say S is to D is equal to C is to T. Since S is greater than D, implies C is also greater than D. Therefore, S is to C is equal to D is to something less than C, which is what we have here. So that was proposition number 2 of book 12 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.